the transient, how to do the transient analysis for an RL circuit. Okay, so this is basically the circuit which we are going to implement today. There is a resistor, there is an inductor, there is a step input, because we have to switch the circuit on, and the mm, at 0.01 second we will get the input as 1. Before that the response would be the input would be 0. That is what we are trying to see here. When you do the transient analysis, we are thinking about a switch which is first it was we are thinking that the first it was open, and then at 0.01 second the switch is getting closed. So that is what we have realized here with the help of this step input. Okay, so then these are the voltage sensors, this is the current sensors, this is the solver configuration, and these are the scopes on which we will get the result. I will show the results also to you first. This is the response which we get of the voltage across the resistor and voltage across the inductor, and this is the response of the current which we are going to get from this particular Simulink model. Okay, so let me just make it for you once again, so that you would be able to implement. Yeah, that's what, see, that's why it was not coming. Okay, no problem. This is your voltage sensors we want. Then we want current sensor. Okay. Then we want resistor. Then we want inductor. Then we want, just double click and you will get this create annotation thing coming. So controlled voltage source we want. Okay, this is your controlled voltage source. Oh no, because we wanted a DC source, I will have to just delete this and control foundation. This one is this one is also current source. I have taken this by mistake. I have to take voltage source. Control voltage source foundation library. Yeah, this one, third one. This one is the correct one. Okay, then we have to take step input. Then this is a Simulink block. We have to connect it to this power system block. Then we will have to have the uh, Simulink to PS converter. Okay, so this is a communication block which will connect this to this block. All right. Then we will rearrange our stuff and make the circuit ready. You just do Control R, so this will get rotated, then connect it. Or don't connect it because we want the current source to come here. Okay. So yeah, now I will connect this current source here. Yeah, and just like this, and this is the second, and then we want the function solver configuration. Yeah, this one, this block we did. Then we want electrical reference block. Yeah, then this will get connected here, this will get connected here, this will get connected here, and we have to find the voltage. So I will take the plus, sorry, the minus will be coming here from the voltage source and the plus will be going here. Similarly, I want one more voltage source to be at the this thing, that is at the inductor's place. So like this the connection is done. Okay, and then I want scope. mm, this scope, and then now I want a PS to Simulink converter, and I want a mux. Okay, so right, so this I need three, so I will just control C, control V. So this portion, this thing, you just control and just control C and control V. Yeah, now it is. Okay. So one more I want. So first I will just keep the voltages of the this thing, that is the voltages are across the resistor and the capacitor. I will want it to be seen in one of the scopes, and the other scope I would like to see the response of the current. Okay, so I will just connect this like it, like this. Okay, yeah, like this. Now this is the uh, exact this model which I have created for you. Okay, this is the transient RF, right? Next, what we have to do is we have to set the parameters. Like step input I want to give at 0.01, and at 0.01 the input will come and the final value of that input would be 0, right? Then we want to give the value of the resistor as 100 ohms, that of the inductor as 20 millihenries. Just do it as 20 20 e to the power minus 3. Okay, so it's 20 millihenry. Next, oh, changed. Yeah, fine. Now we have this model. We'll just run it for 0.025 seconds, and then we will see it. We should get these results. Okay, so I will just close the previous results so that it does not create a confusion. uh, hmm. Just save it once and then just run it. ठीक है, then you see the results. See, this is the voltage across the resistor and the voltage across the inductor, right? So just let me make the style of the plots look good. This one is yellow. Let's just increase the width of that particular line. You can see yellow color is now bit more wider. So okay, next we will PS2, and I'll just 1.5, make the size as 1.5 and let the color be red so that it gets uh, very good view, right? So this is how the voltage waveforms will look. Similarly, if you want to see the current waveform, which is of more importance to us, because we can see the transient response In the case of an RL circuit here, I'm just going to increase its line width again, and maybe I should do it for red color. It's good. Okay. Okay, fine. So we can see that the if you have to find out what is the tau, that is the time constant of this particular system RL circuit. So we know that this would be the response. See, this is the current response. This is the theoretical work which I have which I'm showing you, that like RL circuit is switched in. So the response would something like look something like this, and your tau, that is the time constant for an RL circuit, is given by tau is equals to L by R. It is nothing but the uh, instant at which, that is the point, final values 0.63%, 63.2% your current, while growing the current waveform, when it reaches to 63.2%, what is the value of tau, that is our time constant, right? So we can see that this is the equation for an RL circuit which we get, that is I is equals to I naught into 1 minus e to the power minus t by tau, and tau is nothing but L upon R. So when we start the analysis and we consider that t is equals to tau, then we will get I is equals to I naught into 1 minus e to the power minus 1, that is coming out to be 0.632 times that of I naught. Okay, so for this particular value of inductor and resistance, what would be the tau for our circuit, we have to analyze. So we have taken R as 100 and L has 20 millihenry. So the time constant we should get is nothing but 0.0002 seconds. Okay, so that is what we are seeing, that is this practically coming when we are realizing it through the Simulink model. Okay, so that we can see here, this is the current waveform. This is the response which we are seeing. Okay, so some 63.2% is coming, it would be coming here, and we can easily see that. See this point, it is coming as 2.15. Okay, and it is starting at 0.01, like this here. If you see the data point, I'll show you. Mm, right, you can see that it is starting at 0.01, and at 63.2%, if you are saying it is, let's say it is coming out to 0.010. Okay, you can calculate it and you'll get 0.01015 minus 0.01 is coming somewhere around 0.0002. So this circuit is giving us the same value as we have theoretically calculated. Okay, so that is the main intent of this particular experiment. And while increasing the inductor's value, how the time constant tau is changing, we can see with this experiment how the value of resistance, if you are going to reduce the value of resistance, how the time constant is going to change. We can do all of that with this particular model. Okay, so that I'll give you as an assignment, and I would like you to see the response and uh, give the analysis which you have found out. Okay, thank you. By your own.